Hello, welcome back for chapter 4. We're going to do a little intro activity that hopefully will help you relate from chapter 3 to chapter 4. And that activity starts with this idea right here. The probability of an NBA player making a single free throw is 83%. Make a tree diagram to find the outcomes of an NBA player shooting 3 free throws. So we have shot number 1 could be, I'm going to let S be for success and F be for failure. So S is, he made the shot, which we said is 0.83. And then he doesn't make the shot, which is failure, is 1 minus 0.83 or 0.17. Then we're going to assume that from shot to shot, it's independent. And we talked about independent and dependent events in chapter 3. So if they're independent, let's just make a note of that. Then shot number 2 should also have success and failure at the same rate. And so that means he could make shot 1 and shot 2, or shot 1 and then miss shot 2, or he could miss the first shot and make the second, or he could miss the first shot and miss the second. Okay. Then we have what could be the result after we shoot number 3. And because again, they're independent, there are 2 outcomes for shot 3. Success and failure. So you might be wondering, how can we find out exactly how many total outcomes we should have in our sample space? Well, each shot has 2 possible outcomes. So shot 1, shot 2, shot 3. There are 2 possible ways for him to make each of the shots. So that would make 8 outcomes. Or 2 to the 3rd, which would be 8. So 3 is the number of times you're running the experiment. And 2 is the number of outcomes, number of ways to have each experiment turn out. So let's list our sample space. That's always listed in brackets. So we could have success, success, success. Success, success, failure. Success, failure, success. Success, failure, failure. So it looks like there's 1, 2, 3, 4. There's 4 ways that he would have success on the very first shot. The 1, 2, 3, 4, the last 4 ways are all when he had a failure on the first shot. So we have failure, success, success, failure, success, failure, 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 success, or this would be the worst case scenario, failure, failure, failure. These are not equally likely because the two possible outcomes of shooting the free throw are not equally likely. So let's go ahead and list our possible outcomes. And we're going to say X is, I'm going to list all 8 of them here. Before, so X is, I'm just going to list X as the number of free throws he made. So in this outcome, he made 3 free throws. In this outcome, he made 2, and this outcome 2, and this outcome 1, this outcome 2, this one 1, 1, and 0. Okay, so let's just look at the probability of each of the outcomes individually. So this one would be success, success, success. We can also write that as 0.83 to the 3rd power. And that comes out to be 0.5718 if you round to 4 decimal places. Now, the outcome where we have 2 successes, we have 0.83 squared times 1 failure, 0.17. And that comes out to be 0.1171. And so this outcome here is going to be identical because there's also 2 successes. And this one down here is also going to be identical because it's 2 successes. Then there's 3 outcomes that are going to be 1 success. So that's going to be 0.83 times 0.17 squared. And that outcome probability is 0.0240. And so these are also 0.0240. And then the last outcome of all failures is going to be 0.17 cubed. And that is okay. And let's also note that the exponent on all of these adds up to 3. So the first one and the last one are already 3, but the ones in the middle, we have 2 and 1. Exponent is 3. 1 and 2 exponent is 3. So the 3, remember, signifies that there are 3 trials of shooting the free throw, 1, 2, and 3. So we're doing a lot of review really over the last couple chapters here. I also want to throw out what makes it unusual. Do we have any unusual events? And we said an unusual event has a likelihood of less than 5%. So we would have getting 1, the SFF, and so each of the 1 success those are all 0.024. They're less than 5%. So yes, they're unusual. And then of course the all failure at 0.0049, that one is also unusual. So those are very unlikely. Okay, so we're going to wrap this up into the beginnings of chapter 4. Chapter 4 is all about discrete random variables. So let's go back to our definition of discrete random variable. Discrete random variable is a random variable whose outcomes are counted. Examples are humans, cars, things, computers, coffee cups. A discrete probability distribution lays out all of the actual outcomes. And so we just created a distribution here of the possible outcomes from an NBA player shooting the free throw 3 times. So there are 2 main characteristics that have to be satisfied for a discrete probability distribution. One of them is each probability is between 0 and 1 inclusive. Symbolically, that looks like this. The probability of that outcome has to be greater than or equal to 0 or less than or equal to 1. That's the inclusive. The second is the sum of all the probabilities is 1. And we can show that by this summation symbol. So we're summing up, we're adding up all of the individual probabilities and they have to equal 1. So if we were to go back and add up all of our probabilities from these 8 outcomes, they should equal to be 1. They might be 0.999 depending on our rounding. Okay, so let's look at example 1. It says a child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let X be, what are we counting? X is the number of times per week a newborn baby's crying wakes its mother after midnight. So for this example, possible values for X, or the number of times the baby wakes its mother, is 0 times, 1, 2, 3, 4, or 5. Now they didn't count anything higher than 5. So that's how we define X, and these are the possible values for X. This is what the probability distribution would look like. So what this says is there were 23 out of the 50 mothers whom their baby woke them 2 times in the last week. Okay, there was only 1 mother down here where their baby woke them 5 times. And so this is discrete because discrete meaning each time baby wakes mom is counted. So that's why it's discrete. And then it's a probability distribution because each individual probability is less than or equal to 1 and greater than or equal to 0. And also the probability is total to make 1. If we were to add these, it would be 2 plus 11 is 13. 13 plus 23 is 36. Plus 9 is 45. Plus 4 is 49. Plus 1 is 50 over 50. Okay. Let's look at example 2. Example 2 says, a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. Let X be the number of times a patient rings the nurse, and the values for X are going to be 0 through 5. Again, a patient could ring for their nurse more than 5 times, but only 0 through 5 were counted. So P of X is a probability that X takes on a value of X of 0, 1, 2, 3, 4, 5. And again, we showed you some outcomes here in this probability distribution. And it says, why is this a discrete probability distribution? And again, it's because they are all greater than or equal to 0, but less than or equal to 1, and they add up to be 1. 4 plus 8 is 12. Plus 16 is 28, plus 14 is 42, plus 6 is 48, plus 2 is 50 over 50. Okay, so we're going to go back to our NBA players for just a moment. Let's go back to our NBA players shooting free throws. Suppose the 3 players each shoot a free throw. Oh, that was not supposed to be there. Suppose a player is randomly chosen to shoot 3 free throws. So one player is going to shoot 3 free throws. Let X be, how are we going to define that? The number of free throws successfully made. And what values can X take on? Well, we found that it could take on 0. We go back to our example, 0, where they missed all 3 shots. They could also take on 1 shot, 2 successes, or all 3 of the free throws were made. So we're going to use this scenario and we are going to fill in those probabilities. So they could have 0 successes, 1, 2, or 3. And what are those probabilities? So for 0 successes, we said that was 0.0049. And for all 3, we said that was 0.5718. But 1 success actually happened 3 times, the SFF, the FSF, and the FFS. So because it happened 3 times, the probability of making 1 shot has 3 possible out scenarios that match that. So we have to multiply 0.0240 times 3. And that comes out to be 0.720. And like similarly, to get X equal to 2, where the player makes 2 of its free throws, could happen in these scenarios: success, success, failure, success, failure, success, or failure, success, success. And so we have to multiply the individual probability of 0.1171 multiplied by 3. And so when we do that, we get we get 3513. I think this so I had made an error. I typed this incorrect. The probability of 1 free throw made is 0.0720 because this is 0.0240. I just wrote that incorrectly. So these all add to 1. Okay, let's look at another scenario. Example 4. Suppose Nancy has classes 3 days a week. She attends classes 3 days a week, 80% of the time, 2 days, 15% of the time, 1 day, 4% of the time, and no days, 1% of the time. Suppose 1 week is randomly selected. Let X be the number of days Nancy attends class. X takes on what values? They go in brackets. So it looks like she could go 0 days, 1 day, 2 days, or all 3 days. So if 1 day is chosen random, 1 week is chosen randomly, construct a probability distribution like we did in example 1, looked at in example 1. The table should have 2 columns, X and P of X. And what does the column P of X come to? So we've got 0, 1, 2, and 3. And it says that she attends no days 1% of the time. So that's 0.01. Attends 1 day 4%. Remember, the percentages are always going to go in decimal form. 2 days is 15%. And 3 days is 80%. and they add up to 0. They sum to 1.0. So let's try to answer an individual question about this. So it says, what is the probability that she attends class at least 2 days a week? So at least 2 days a week. In your formula packet for class, there is a table with different wording for these inequalities that will help you. So this would look like this. Probability of x is greater than or equal to 2. At least 2 means 2 or more. So 2 is included. So that means we're adding 0.15 plus 0.80 to get 0.95. 95%. What is the probability that she attends class no more than 3 days a week? So no more is the probability that x is less than or equal to 3 days. No more means not more, but including three. So that means we're including 0. So 0.1 plus 1, 0.04 plus 2, which is 0.15 and 0.8, which is equal to 1. Okay. Let's look at example 5. Example 5 says, Jeremiah has basketball practice 2 days a week. 90% of the time he attends both practices. 8% of the time he attends one practice, and 2% of the time he does not attend either practice. What is x and what values does it take on? So x is number of days attending practice. And the values it can take on are 0, 1, and 2. And so we're going to fill in our probability distribution. So it says 0 days is 2% of the time, so that's 0.02. And one practice is 8% of the time, so 0.08. And 90% of the time, or 0.90, he attends both. So C says, what is the probability that Jeremiah attends at least one practice a week? At least one is a probability that x is greater than or equal to 1, so including 1 or more. So we could add the probability of 1 plus the probability of 2, which would be 0.98. Or remember that at least one that we learned about in chapter 3, we could do 1 minus the probability of 0, because that's our complement. So we could also say 1 minus 0.02 to get 0.98. So what is the probability that he attends class less than 2 practices a week, or attends practice, sorry, attends practice less than 2 practices a week? And that is a 10. So let's look here. Probability of x is less than 2. So not including 2. So that would be 0.02 plus 0.8 is 0.01. So about 10% of the time, he doesn't practice both days. That wraps up 4.1. Catch me back for 4.2.